All right, so let's try to pick up our class. I know that I went over some of this kind of modular arithmetic and divisibility rule stuff after the test on Thursday, ages ago. So I'm going to go back through it. Okay, so what we are doing is we're starting a new chapter, which is on modular arithmetic. So essentially what modular arithmetic is it's a new system of arithmetic, namely addition and subtraction and multiplication, but it's using a different number system than the integers like we're used to. So modular arithmetic is also called kind of like clock arithmetic, and the basic idea is that you're working with some finite set of numbers and you define a new addition and multiplication on that new set of numbers. But it's not so strange as you think. It's really just like looking at the clock. So for instance, if it is 2 o'clock right now on a clock that has numbers from 1 to 12, if it's 2 o'clock right now, one could very reasonably ask, what time will it say on the clock in 13 hours? Well, in 13 hours, we know that the clock has 12 different points. Once you go through all the 12 points, you'll get back to 2. And then if it's 13 hours, you'll go 1 hour further, so you'll be at 3. So in modular arithmetic, if I'm looking mod 12, mod the clock, then 2 plus 13 is equal to 3. We're going to go through this very carefully, but that's essentially the idea of what we're trying to set up. We're trying to set up a version of arithmetic using a different collection of numbers. And the very first thing that we want to do when we set up this modular arithmetic is we need to understand divisibility inside the integers. So that's where we'll start. So start with our definition. Let's take A and B in Z. Let A and B be integers. And let's take A not equal to 0. Then A divides B in the integers if there exists a C inside the integers such that B is equal to C times A. We use the notation A with a vertical bar with a slash through it for A does not divide B. Okay, this is a very reasonable definition, and we can kind of check that it makes sense with some examples. Let's consider 5 dividing, I don't know, 30. Does 5 divide 30? And the answer is yes, 5 does indeed divide 30. The reason that it divides 30 is because I can write 30 as being equal to 6 times 5. So in this picture, the C that I found, this integer that I produce, is 6, such that B, namely 30, is equal to 5 times a particular integer. So indeed, 5 divides 30, as we expect. And moreover, 5 does not divide 31, because there's no integer that I can find such that 5 times that integer is equal to 31. In other words, 31 over 5 is a rational number, but not an integer. Okay? So, one important thing to note is that there's some things that we should remember. any number a always divides 0. Everything divides 0 because 0 can always be written as a times 0 for any non-zero a. So just remember, I only demand that a is not equal to 0. B can be 0, and that's just fine. Okay, with this in mind, there's a very basic and natural theorem that comes to mind. Theorem if a divides b and a divides c, then a divides b plus c. So an example of this is if I know that 5 divides -5, and I know that 5 divides 15, then it is true that 5 divides -5 plus 15, or that 5 divides 10. Right? The basic idea is I'm essentially factoring. If I know that -5, so -5 is equal to -1 times 5, and 15 is equal to 3 times 5. So when I'm asking, does 5 divide -5 plus 15, I'm saying, can I write -1 times 5 plus 3 times 5 as some integer times 5? And the answer is yes. -5 plus 15 is equal to -1 plus 3 times 5. So whatever it is, it's divisible by 5. Okay, and this one, you prove it in pretty much precisely the same way. Proof, if a divides b, then b is equal to k1 times a, where k1 is some integer. If a divides c, then c is equal to k2 times a, where k2 is some integer. And now I can write b plus c is equal to k1a plus k2a, which is equal to k1 plus k2a, so a divides b plus c, because I can write b plus c as some integer times a. Pretty straightforward. It is a tragedy that you can't tell me when my writing is illegible anymore. I'm sorry about that. Next part of the theorem is that if a divides b, then a divides bm for all m in Z. This is just saying if, I don't know, let's do 3 now. 3 divides 18, which we know is true, because 18 is equal to 3 times 6. If 3 divides 18, then I know that 3 divides 18 times any integer. I don't know what integer to pick. 1, 1, 2, 1, 0, 3, 2. Who cares? I pick any integer, and I know that 3 will divide this big product. Because I can always write this big product, 1, 1, 2, 1, 0, 3, 2 times 18 is really equal to 1, 1, 2, 1, 0, 3, 2 times 6 times 3. I have shown that this number can be written as some integer times 3. And the proof is doing this with symbols instead of 3 and 18 and some random number. And then the last part of the theorem is that if A divides B and B divides C, then A divides C. So this is a little bit of a transitivity property. And the proof of this is just following your nose. It's straightforward. We can either do it with symbols or we can do an example, and let's do an example, why not? So for instance, we know that 3 divides 21, and I know that 21 divides 63, and this indeed is going to imply that 3 divides 63. So these two imply 3 divides 63. And the reasoning is pretty simple. The thing is, I was able to write 21 as being 3 times 7, and I was able to write 63 as being equal to 3 times 21. And now I just substitute. Maybe I should have picked 4 times so that this 3 isn't confusing. The point is I just plug in this 21 over here, and now I'm able to write 63 is equal to 3 times 7 times 3. And it's this last 3 that I'm using to see that 3 indeed divides 63. If I had picked 84, it'd be a nicer example, because then I'd have 4 times 7 times 3. So this extra 3 is maybe a little irrelevant. And the proof in general essentially just says replace all the numbers here with the correct letters, and everything goes through. As a corollary, this is just a nice corollary to remember. If A divides B and A divides C, then A divides MB plus NC for all M, N in Z. So for instance, if I know that 3 divides 18 and I know 3 divides 84, then what I can do is I know automatically that 3 divides whatever terrible number I put here, like 587 times 18, plus, I don't know, negative 207 here times 84. Automatically, I can put any integers inside these parentheses, and I know that 3 will always divide this big sum and product, and this corollary just comes from parts 1 and 2 of the theorem. Great. These are probably not too unexpected. It's just kind of the regular divisibility that we're used to. Okay. Next, let's talk about the division algorithm. Division algorithm. So essentially, what we have noticed, and it's offensive to us, that not every integer divides every other integer. It simply isn't the case. 5 does not divide 31. So the idea that has been around since antiquity is that what we should keep track of is the remainder. We should try to divide 31 by 5, get as close as we can. So for instance, 5 divides 30. Keep track of that 5 divides 30, and remember that 31 is just 1 off from 30. There's just some remainder when we try to divide 31 by 5. So the division algorithm essentially says there's a well-defined procedure for producing nice remainders when we divide in the integers. Okay. So here's what the division algorithm says. So let A be an integer, and let D be a positive integer, so in z greater than 0. Then there exist unique integers q and r in z with a special added condition. We're going to demand that r is greater than or equal to 0 and less than d, such that a can be written uniquely as d times q plus r. So there are names associated to each of these. A is the dividend. I don't know if you can see what I'm writing all the way over there. Probably not. But anyways, A is the dividend. D is the divisor. So A is the number that I'm trying to divide by D, trying to divide the dividend by the divisor. Q is the quotient. And R is the remainder. And notice this very important and special property. I'm always going to demand that the remainder is a positive integer which is less than the dividend. So the theorem says that this is unique. A treatment of this is in the book. I don't want to prove it at the moment. We can probably come back and prove this when we have induction. But for right now, let's just take this as a theorem. And let's start working on some examples. So for instance, let's take A is equal to 101 and D is equal to 9. I picked two integers, 101 and 9, and I'm trying to divide 101 by 9. And 9 does not divide 101 precisely on the nose. Okay, that's fine. What the division algorithm tells me is that I have some sort of best way of getting close. I'm always going to be able to write 101 as being equal to, well, I'm going to find a close number below 101 such that 9 does divide it. A close number below 101 is 99. And 9 does indeed divide 99. It's 9 times 11. So 101 is equal to 9 times 11 plus the small remainder of 2. So the idea is I got as close to 101 as I could using multiples of 9, and then I keep track of the remainder. There's a very graphic way of visualizing what's going on using the number line. So let's think about dividing 7 by 3. So visually, what I'm thinking about when I do this modular arithmetic is I'm picking out all of the multiples of 3. 0 is a multiple of 3. So 0, 1, 2, 3, 4, 5, 6, and then 7. So if I want to understand what 7 is when I divide by 3 in the integers using the division algorithm, well, I'm going to count up using these multiples of 3. So 3 here, there's a 3 here. I get as close to 7 as I can underneath, namely 6. And then the remainder, what's left over, is just this 1. So this is the visual picture for writing 7 is equal to 2 times 3 plus 1. This is the dividend, 3 is the divisor, 2 is the quotient, and 1 is the remainder. Okay? Fairly natural picture. Let's do another example. There's no good way to space this out. Let's now do -4 divided by 3. Okay? So I'm going to draw the same number line, and I'm going to remember what all the multiples of 3 are. 0 is a multiple of 3, or 3 divides 0. I got -1, -2, -3, -4. But what I have to do is go past it. So I have -4, -5, and then -6. The point is that the remainder always has to be a positive number. We're selecting R so that it's always positive, which means that when I try to understand -4 divided by 3, I count down in tuples of 3. Here's -1 copy of 3, a -2 copies of 3, and then I add 2 on the end. So, in other words, -4 is equal to -2 times 3 plus 2. And the remainder of -4 divided by 3 is 2. Positive number, greater than or equal to 0, less than 3. Okay? So it's probably good to keep in mind this fact that you're always thinking about the multiple of 3, or whatever your divisor is, that is the closest to your number and also below your number. And then you count up when you count the remainder. Let's do one more example of this sort of thing. We can do it over here. Let's think about now switching terms. Instead of dividing 7 by 3, let's divide 3 by 7. Once again, I draw my picture. 0 is a multiple of 7. And then I count 1, 2, 3, 4, 5, 6, 7. And what I look for is the largest multiple of 7 that is below the number that I'm interested in, namely 0. And then I add the remainder. I add up. So 3 is equal to 0 times 7 plus 3. 3 is the remainder of 3 divided by 7. And the quotient is 0 in this case. Okay, hopefully this is manageable. Let's move on to some more modular arithmetic. 13 minutes left. Okay. So the first thing that we want to do is add some notation. Which is as follows. So if A is equal to dq plus r, with r greater than or equal to 0 and less than d, then we write A is A mod d is equal to r. So what I'm essentially setting up here is I'm defining a function called mod d, which only keeps track of the remainder of any number A mod d, or modulo d. So, the notation is this. If we have in the division algorithm the expression A is equal to dq plus r, then I write A mod d is equal to r. This is really defining a function from the integers to the set of numbers from 0 to d. Well, 0 to d minus 1, actually. So let me just do a quick example. So let's consider the function mod 4. And this is a function from z to the set of numbers 0, 1, 2, 3. Let's start somewhere. So let's try to think about what mod 4 does to 7, say. 7 mod 4. What's the remainder of 7 after we divide by 4? Well, it's 3. So 7 gets mapped to 3 under the mod 4 function from z to this set of numbers. Let's look at 8 mod 4. Well, 4 perfectly divides 8, so the remainder is going to be 0. 9 mod 4 is going to be equal to 1. 10 mod 4 is going to be equal to 2. 11 mod 4 is going to be 3 again, and so on and so forth. So you can see now where the notion of a clock is coming in, right? If I had taken mod 12, then I'd be exactly describing the same problem that I was talking about at the beginning of this lecture, where you're asking, if it's 5 o'clock right now, in 80 hours, what time will it say on the clock? Really, what that's just asking is, what is 4 plus 80 mod 12? Or what is 84 mod 12? The answer is probably, well, I don't know. I don't want to calculate it. Great. So this is our notation. A mod D is equal to R. And now we can get started with some modular arithmetic. Modular arithmetic. Okay, what we're going to do is the following. Let A and B be integers, and let M be some positive integer. So M is in z greater than 0. What we're now going to define is something called congruence. And congruence is essentially the math that results when you only care about remainders. So it's more of the same thing. So definition, we define A is congruent to B modulo M if M divides A minus B. So the first thing to notice, and also if M does not divide A minus B, then we write A is not congruent to B modulo M. The first thing to note is it looks like this definition is lopsided because I picked A minus B instead of B minus A. But something important to notice is that if M divides A minus B, then M also divides B minus A and vice versa. So it didn't matter which order I picked to subtract. It's irrelevant. Okay, so let's do some examples. Let's do some questions. Is 7 congruent to 1 mod 5? So what I'm really asking here is, does 5 divide 7 minus 1, which is equal to 6? And the answer is no. So 7 is not congruent to 1 mod 5. However, I can find a different number which is congruent to 7 modulo 5. For instance, is 7 congruent to 22 modulo 5? So once again, what I'm really asking here is, does 5 divide 7 minus 22? 7 minus 22 is negative 15. So does 5 divide negative 15? Yeah, negative 15 is equal to negative 3 times 5. So yeah, 5 does divide negative 15. So 7 is congruent to 22 mod 5. Let's do one more example, say. Let's consider 10 is 10 congruent to negative 2 mod 3. So really, again, what I'm asking here is, does 3 divide 10 minus negative 2, or does 3 divide 12? And the answer is yes. So 10 is congruent, is congruent to negative 2 modulo 3. So what you're probably picking out is that two numbers were congruent modulo another number if they have the same remainder when you calculate 7 mod 5. 7 mod 5 is 2, 22 mod 5 is also 2, and these numbers were indeed congruent. 7 modulo 5 is 2, but 1 modulo 5 is just 1. The remainders are different, and so these two numbers are not congruent modulo 5. It's the same thing with 12 and negative 2. The remainder of 10, when I divide it by 3, is 2, and the remainder, or is 1, sorry. 9 plus 1 is 10. And the remainder of negative 2, when I divide it by 3, is also 1, because the largest the largest multiple of 3 that is below negative 2 is negative 3, and then you add 1 to get to negative 2. So these two are also have the same remainder modulo 3, and thus they're congruent. And indeed, that's a theorem that we should prove. The theorem is A is congruent to B modulo M if and only if A modulo M is equal to B modulo M. I want to point out something here, because there are two ways that we're kind of using modulo M, and they're very closely related, but they're slightly different. So when I put one number modulo M, this is a function. Here I'm treating mod M as a function from Z to the numbers 0, 1, 2, 3, all the way up to M minus 1. So here mod M is a function. Here, this whole statement is just a statement. This statement is either true or false. Either these two numbers are congruent modulo M, or they aren't congruent modulo M. So technically what's being done here is the setting up of an equivalence relation, which we'll get to later. But it turns out that they're very closely related in this fashion. A and B are congruent modulo M if and only if they have the same value under the function mod M. Okay? So the proof, this is an if and only if statement. So we'd have to prove two directions. The first direction is assume that A is congruent to B modulo M, and then show that A mod M is equal to B mod M. And then the second part of the proof is to assume that A mod m is equal to B mod m, and then show that A and B are congruent modulo m. Let's do one direction of the proof, and I'll leave the other direction to you. So let's assume that A is congruent to B modulo m. What does this mean by definition? By definition, it means m divides A minus B. So m divides A minus B. What does this mean? Well, it means I can find some number c such that A minus B is equal to c times m. Thus, there exists a c in Z such that A minus B is equal to Cm, or A is equal to Cm plus B. Okay, so now I have some nice relationship between A and B. Their difference, well, yeah, their difference is divisible by m. This is what I get from my assumption. So now I want to check that A mod m is actually equal to B mod m. So B mod m means I use the division algorithm on B, and I produce some remainder. So by the division algorithm, I can always write B is equal to Q, the quotient, times M, plus some R remainder, where 0 is less than or equal to R is less than D. I just get this by the division algorithm, and so in particular, B mod M is equal to R. Whatever R is. I know there's some R such that B mod M is equal to R, and it comes from a division algorithm equation of this type. So now what I want to show is that A is also has remainder R when I divide it by M. So A is equal to Cm plus B, and I also know B is equal to Qm plus R, so A is actually equal to Cm plus Qm plus R, which is actually equal to M times C plus Q plus R, where once again, 0 is less than or equal to R is less than D. I haven't changed R here. So I've written A as being equal to some integer times M plus a remainder, which fits the bill of being a remainder. Thus, A mod M is equal to R. So A mod M is equal to B mod M, and we've finished one direction of the proof.